So we are about to start. I would like to invite our first speaker, who is the first this morning, but already the second time here in our conference, Professor V.S. Subrahmanian, Professor of Computer Science at the University of Maryland and the heads of the Center for Digital International Government. Subrahmanian developed big data analytics, including methods to analyze vast bodies of text, learn models of behaviors, entities for data forecast actions by these entities, and methods to influence these behaviors. He was elected as a fellow of both American Association for the Advancement of Science and the Association for the Advancements of Artificial Intelligence. I think that last year we heard about the first global measure of cyber vulnerability of countries around the world, and probably this time you will say something about this as well. Please.
Thank you. Thank you very much, Yaniv, and good morning to everybody in the room. It's a pleasure to be back in Israel and to address this fantastic conference. So let me start by saying, as Yaniv mentioned last year, I spoke about the Global Cyber Vulnerability Report. That was an analysis of about 20 billion malware reports provided by Symantec, looking at about 4 million hosts per year over 2 years. I'm going to use the same data this time, but instead of talking about the cyber vulnerability of countries, I'm looking at the problem of, given a piece of malware and a particular country, how accurately can we forecast the expected number of infected hosts that is infected by that particular piece of malware. So again, a big thank you to Symantec for letting us have access to this data, which is an unbelievable data set. I do want to say that Symantec collected this data from, on an opt-in basis from customers of Norton Antivirus. So all the data that we saw was anonymized by Symantec. So hopefully we're not violating anybody's privacy or doing anything inappropriate. The data itself consisted of 2 data sets that we used. One consisted of binary reputation data about binaries that are present on host computers on which Norton Antivirus is running. The second was antivirus telemetry, telling us things about various kinds of malware recorded on these machines, the time at which it was detected, etc. There's actually one more data set we use that I have not put on my slides, and that's the National Vulnerability Database maintained in the US by NIST, the National Institute of Standards and Technology. And the reason for that is, will be clear in a few minutes. Now, in the data, so that was the talk I gave last year. So last year we looked at 44 countries, including all the major developed and developing economies. This year, we only took a subset of this data, about 1.5 million hosts, and we looked at the 40 countries with the highest GDP. And the question was a more technical one this year. Last year was situation awareness. What's going on in all these countries? And who's the most cyber vulnerable? And we measured cyber vulnerability along 2 axes. One, the percentage of machines in the country that are infected by at least one malware. And 2, the average number of pieces of malware on a host. That's what we did last year. The countries that turned out to be the most cyber vulnerable last year, depending on how you counted and which year we looked at, were India and South Korea, both basically trading off for the spot of being most cyber vulnerable. The safest countries last year were, this is data that pretty much holds, included primarily the Scandinavian countries, Norway, Denmark, Sweden, etc. Okay? So this year, we looked at a very different data set. We looked at the 50 in the entire wine data that we had access to, the Symantec wine data. We looked at the 50 most prevalent pieces of malware. So we didn't look across the board in the study I'm talking about today at all malware, only the 50 most common ones. Okay? The 50 malware that infected the most machines in the data. And we only looked at the 40 countries with the highest GDP. Sorry if your country was left out, but we couldn't look at everything, and my apologies. So let me say a little bit about the 3 kinds of unusual spread patterns of malware that we saw. So if you look at these charts, these are just some examples. What you see is the number of days of data. Actually, we had a total of 640 days that we looked at. And you see that on the x-axis. And what we did was to split this data into a part from which we learned our predictive models and a part where we tried to predict. Okay? You're not seeing any predictions on this right now. But what I'm showing you are some general trends. We saw, in addition to the usual trend, which I've not shown on these slides, where you expect the data in the testing period to reflect the same distribution or same time series as you expect in the training data, what we saw were 3 very interesting trends. And these are just some examples. In one, you see a gradual increase in our learning data, but in our test data, you see a very different trend. So the vertical line that you see in all the charts I'm going to show in the next few slides separates the training data from the test data. So for predictive models, predictive model, to me, is completely useless if you can't use it to make real predictions, all right? And that means that we need to learn the model from a sample of data and test it on data that the algorithm has not seen previously. So everything to the left of the vertical line, the red line that you see on both graphs, is learning, and everything to the right is testing. And I've just shown that on one slide, but please keep that in mind for future slides. So one pattern we noticed is one where there's a significant increase in the percentage of infected hosts by this particular malware. In this case, a particular malware. This looks at country US and a particular malware with a certain ID. Symantec was very reluctant to disclose the identity of the malware to us. So while I have some guesses, I'm following their protocols on what the malware ID was. Okay? So you see here is a very steep curve going upward, and then a steep drop-off in the testing period. How can we predict that? Another key pattern is one where we see a gradual decrease and then a somewhat gradual increase in the testing period. So a standard, simple model will not get this. And then, of course, you see something where there's a trend that continues from the test data to the the data you learned from, the training data, to the data you actually are trying to predict. So you see a smooth decrease. And of course, there's a corresponding graph which shows a smooth increase. I'm not showing that. So we want to be able to predict all this stuff. So of course, when we try to predict how a piece of malware spreads, it depends on a lot of factors. The intrinsic nature of the malware is certainly one thing. How virulent is it? How common is the software that has vulnerabilities that the malware exploits? These are all obviously factors that play a role. So the malware is one factor, the nature of the malware, but we typically don't have access to too much about that. 2, the nature of the environment, that is the hosts, what software is installed on the host, what operating system are they using, et cetera, et cetera. But 3, there's also information about the behavior of the host. So actually, let me sort of ask a quick question. On average, how long does it take between the time a patch is released for a piece of malware to the time that the patch is actually applied in enterprises or in the private sector? 3 months?
6 months, please.
6 months at least? Any other guesses? All right, so you guys know what you're talking about. Very good. The number we saw was somewhere around 4 months in the data, okay? Which is, right in that ballpark. So you're talking about 4 months when an attacker has, you don't have to do much, okay, if you're an attacker. You wait and say, okay, when is NIST saying this vulnerability exists? When is a patch released? And guess what? There's some time gap between the time a vulnerability is detected to the time a patch is released, and then you still have, on average, 4 months to exploit it. So if you're an attacker, life is good, okay? If you're a defender, we all know is a very tough job. So we said, okay, the National Vulnerability Database tells us information about patches. and about vulnerabilities. It tells us approximately, it gives us a score of the impact of these vulnerabilities. I mean, I know my friends at Symantec argue with the scoring mechanism. I won't get into that. But they do assign a score to the impact that the vulnerability will have if it's exploited, number one. And number two, the difficulty for an adversary to exploit that vulnerability. All right? So I'm not going to get into whether I agree or disagree with those, but any measure is controversial. So what we did was we defined a very large number of features, and we also defined a lot of derivative models. So for example, how many of you are familiar with the SIR model of spread of diseases in epidemiology? Okay, a few hands. So SIR stands for susceptible, infected, and recovered. And what it tries to do is to look at a population of human beings, and it says, well, look, can I define how the number of susceptible people at time t plus 1 is going to change based on the number of people who are susceptible at time t? And similarly for the number of infected people and the number of people who recover from an infection. In this case, we had to look at several other features. I'm being told I have 5 minutes, so let me speed up.
Can I waste 20 seconds?
Yeah, sure.
But, I mean, I'm just a regular user, okay? Then I have an automatic update overnight. So that wasn't 6 months. I mean,
okay, so patches are deployed in several different ways, okay? So to give you an example, there are some users who get automatic patches when they're released, okay, number one. And the trend increasingly is to automate the downloading of patches. Right? There are other applications where the patch requires a manual intervention. So you would be prompted, and if you click yes, the patch is applied, okay, downloaded and applied. And the third model requires manual patching, which happens more often in large enterprise systems, okay? So, you'd be a good guy in this equation. The data we saw showed, on average, about 4 months.
I'm only a good guy because I actually came to a few of these conferences and realized that
Exactly. So let me say a little bit about, so one thing we did was to adapt the SIR model of disease spread, and we built several models that tried to estimate the number of susceptible, infected, detected, and recovered machines. So basically, a machine is susceptible if there's a vulnerability in it. We know what times those are happening. Vulnerability is detected if the NVD announces that this vulnerability exists. It's patched if we see that a patch has been applied in the Symantec data. And it's assumed to be recovered after the patching time. So we basically modified the model. We had to learn a lot of parameters. And here are some examples of what we were able to do. So this shows you, again, just one particular malware ID. Our model is shown in green. The blue line, which you can't see too well here, is actually you can see it on the top right inside that space. And you can see that the green line, which is our model, mirrors the blue line pretty well. The closest competitor in this space is a system called Funnel by my friends at Carnegie Mellon. And that's the pink line here, which you see shows a good trend, but not as close to the blue line. Okay? Here's an example of this kind of thing applied again to selected countries. And I'm going to sort of ask you a couple of questions about countries. So again, simple story. We're able to predict very well. If I look at the Pearson correlation coefficient between the number of machines we predict to be infected in the testing period and the actual number, it's over 0.9. So that shows that we're not saying I can predict that this machine is going to be infected. What we're saying is, can we predict the number of machines that are going to be infected during a given time period? So let me ask you a quick question, and I'll say a little bit about Israel as I'm here if I don't get kicked off the stage. So, I picked 5 countries. So China, India, South Korea, UK, and US listed in alphabetical order, okay? So no bias of any sort, okay, here. And if I look at the 50 most common pieces of malware, who do you think is doing the best job in patching them and in handling the most common pieces of malware? This is different from saying all malware. And by the way, I won't give credit to the countries, governments in this case, but more perhaps to the population. So,
South Korea.
South Korea is doing the best job? All right. China? Okay. So, all right, you only have 5 choices, so that's 2 already. So let me say a little bit. So, So if I look at the, okay, let me sort of show you what's going on, okay? So last year, when I talked about these countries, India and South Korea were at the bottom in terms of being, were the most vulnerable, all right? But that was to all malware, not the 50 most common ones. What you see here is India and China are right down here. I'm sorry, India and South Korea are down here, okay, down here towards the bottom. The US and others and UK are closer to the upper part of these curves. So what that suggests, so what does that suggest? So it suggests that the US is actually doing a worse job than India and South Korea in patching the 50 most common malware. And the first thought I had was we made a mistake, all right? Because our previous study showed that the US was actually much safer than India, South Korea, and China for that matter, okay? So even though we heard the US ambassador say the US is the most attacked country from a cyber perspective, that's partly true, but largely because the number of devices in the US is much higher than many other countries, okay? So if you actually do it on an average infection per country or the percentage of infected hosts, the US actually is about the 12th most safe country, after the Scandinavian countries and countries like Germany and Switzerland and so forth. So here we said, well, there seems to be a contradiction. Why is that? And this is an example of India. So I'll tell you why we thought it was the case. I can't sort of validate this, but the data certainly supports it. But I can't say this is the only correct hypothesis. So my hypothesis explaining this is that security managers in India, in South Korea, actually do a pretty good job at patching the most well-known vulnerabilities. But they do a less good job in patching all the other vulnerabilities. And therefore, the reason the US does much better than South Korea and India across the entire spectrum of malware is because their overall patching strategy is much better. Overall, education of the population is much better. But in fact, Indian and South Korean security managers perhaps concentrate more on the most potent threats or the most virulent threats that they know about. So they don't patch everything properly. All right? So here's an example of how we can predict this. For India, let me say a little bit about Israel for a moment. So you can see here that, so here what you have to do is to look at the y-axis, which is the percentage of infected hosts. And this is aggregated across many different pieces of malware. And what you see here is that Israel levels out at somewhere around 0.04, 004, whereas and India, for instance, levels off a little below that. So what that suggests, again, is that, contradicting what people think usually, security managers in India are doing a better job defending against the 50 most potent threats, but doing a much worse job defending against everything else. Okay? So anyway, so I'll stop there as I'm out of time. But thank you very much.